In recent years, scientists have recorded deep seismic signals beneath the Pacific that do not behave like those from solid rock. The patterns are still under investigation, but some resemble the echoes that can form in large underground cavities. Such anomalies often prompt follow-up expeditions, much like the documented extreme cave dives and trench explorations that have revealed environments once thought impossible for life. Coupled with accelerating advances in radar mapping and subterranean surveying, these findings are drawing mainstream attention to the planet's unexplored depths. And in early 2025, one global report would show just how far that exploration had advanced. The 2025 boom in underground exploration. By the start of 2025, researchers and exploration groups were documenting an unusually sharp rise in successful cave surveys, deep mining reconnaissance, and subsurface mapping. The growth wasn't confined to one country or driven by a single discovery. It reflected a combination of factors. Industry reports on the global cave diving market showed a marked increase in expeditions being planned and funded, while coverage in specialist outlets like Shearwater noted a swelling community of technical divers and speleologists exchanging data more fluidly than ever before. Advancements in sensing equipment, particularly compact, multi-channel arrays and drone-mounted ground-penetrating radar, were shortening the time needed to produce usable maps, even in difficult conditions. These systems, developed for rugged or hazardous terrain, were deployed from deserts to polar ice, operating where human access had once been slow or risky. Part of this surge came from the deliberate coordination between national surveys, academic labs, and private operators. In earlier years, valuable subsurface data often sat in separate databases or paper archives, making broad comparisons difficult. By 2025, shared platforms and standards meant that data from a Greenland ice cave scan could be cross-referenced with karst system imagery from central Mexico, sometimes revealing structural parallels that would have gone unnoticed. Field crews equipped with imaging units small enough to fit in a backpack could send three-dimensional models in real time to off-site analysts, who then advised on which passages merited direct exploration. This approach not only reduced the likelihood of bypassing concealed voids behind collapses or fissures, it allowed for rapid reallocation of resources when conditions changed. Several documented field projects stood out, both for their difficulty and for the insights they offered. The BBC covered J2 cave descents in Mexico, in which technical dive teams led by Phil Short reached submerged chambers far deeper than conditions had suggested possible, provided a rare look at flooded systems with complex hydrology. Meanwhile, National Geographic's expeditions into Greenland's Wolfland ice caves revealed melt-carved interiors so extensive that internal acoustic mapping was needed to plot their extent. In both cases, the discoveries upset earlier assumptions about how such environments evolve, forcing model revisions about climate, water movement, and structural stability beneath ice or mountains. These were representative of the kind of fully documented surprises now emerging each season. As the datasets from these and other expeditions grew, so did efforts to link field results with broader geophysical measurements. Recent seismology research, including new modeling ideas from studies of Earth's deep interior, has encouraged teams to examine whether certain low-frequency or damped seismic patterns correlate with the locations of mapped cavities. While this is still an open question and not yet a proven mapping method, targeted surveys informed by seismic clues have shown promise in focusing searches. In a few cases, ground-penetrating radar crews were dispatched to sites earmarked by these patterns, and they returned with usable maps of voids matching the rough scale suggested by the seismic interpretation. The work is iterative, and the scientific community is careful to stress that many anomalies turn out to have unrelated causes. Yet the potential for integrating the two approaches is driving active collaboration between seismologists and cave surveyors. The same link between technology and strategy is changing how expeditions are planned. Instead of evenly distributing effort across large, unmapped areas, modern teams increasingly prioritize places where multiple lines of evidence converge. Historic reports of unusual subsurface formations, unexplained density readings, or subtle anomalies in long-term seismic monitoring. Where older campaigns might spend weeks clearing collapsed entrances or probing dead ends, project leads now arrive with layers of preliminary data hinting at which directions hold the greatest promise. This has already produced a series of efficient, high-yield missions in Europe, the Americas, and Asia, where networks of passages were charted in a fraction of the time earlier techniques required. Underlying these rapid gains is a gradual shift in how subterranean environments are understood. For decades, geologists regarded large, stable voids in the crust as exceptional and largely confined to specific geological contexts. The accumulation of new maps, whether from ice, volcanic rock, or sedimentary formations, suggests such structures may be more common and diverse in origin than assumed. Some seem to align with known fault lines or remnants of ancient volcanic plumbing. Others have no obvious link to local tectonic history. The emerging picture is less one of uniformity and more of a varied subsurface terrain, where both slow geological processes and sudden events leave behind complex architecture. These insights are not just of academic interest. Knowing the distribution and character of large voids has applications in resource planning, environmental monitoring, and hazard assessment. In water-scarce regions, for example, enclosed cavities can serve as reservoirs or influence groundwater movement. In others, their stability or instability can affect building safety and land use. Because of this, there's growing interest in establishing more complete catalogues that record each mapped void size, depth, and environmental conditions. Such a record would be invaluable for comparing patterns across continents and for testing hypotheses about their formation and longevity. Even with the acceleration in mapping, researchers acknowledge that what is now visible may be only a fraction of what exists. New tools reveal more in the areas that are actively surveyed, but large portions of the planet's interior remain logistically out of reach. Efforts are underway to adapt aerial and orbital sensing, already proven in archaeology and geology on the surface, to detect indirect signs of subsurface architecture on regional scales. Combining such data with on-the-ground verification could, in the future, greatly expand the known map without requiring exhaustive manual exploration in every location. What unites the events of 2025 is this intertwining of technological capacity and cooperative networks. The pace of mapping has increased where these conditions overlap, and the information gathered has begun to refine not just where further exploration should occur, but why certain formations appear where they do. In this growing body of evidence, physical measurement meets interpretation, and interpretation sometimes reopens questions that seemed long settled. Occasionally, these questions extend beyond geology into other domains, raising the possibility that observations made centuries ago, recorded for entirely different reasons, might now be examined under a new light. When ancient myths sound like geological reports. Among the expanding troves of subterranean survey data, a smaller but no less intriguing trend has been emerging: comparisons between physical cave environments and descriptions preserved in oral or written traditions. In 2025, this line of inquiry began to take on a more systematic character, with researchers compiling multilingual myth archives and cross-referencing them against geological records. The question wasn't whether myths were literal maps, but whether some carried enough consistent environmental detail to serve as mnemonic guides to specific types of underground terrain. One of the most discussed examples involved National Geographic's documentation of Greenland's Wolf Land ice caves. In addition to their striking interiors, the caves yielded speleothems whose chemical composition captured paleoclimate records stretching back thousands of years. For glaciologists, this was hard evidence that enclosed subterranean environments had long stored clues about surface conditions. For anthropologists, it suggested a possibility that ancient inhabitants, aware of such environmental constants, may have encoded their knowledge in descriptions that survived as oral accounts. A description of skyless halls where the air carried the taste of cold stone, for example, might match what a traveler encounters inside such an ice cave, and the environmental markers, darkness, unchanging chill, the soundscape, could persist across generations of retelling. Archaeologists familiar with similar phenomena in other regions began revisiting long-dismissed refuge stories. In South America's Andean highlands, several communities maintain origin accounts that include moving into the earth during a period of unlivable surface conditions. The details vary, but some narratives specify extended movement through enclosed spaces and an auditory shift described as the outside gone silent. These are not proof of any one event, but offer details that can be tested. Using low-frequency ground-penetrating radar and portable gravimeters, equipment now compact enough for remote use, survey teams can quickly determine whether voids exist near the locations named in the stories. Findings are uneven, but in a few tested sites, geological signatures consistent with substantial underground cavities have been recorded, prompting further exploratory proposals. The database approach marks a shift away from relying on singular, sensational finds toward broader pattern analysis. Folk traditions from Central Asia, for instance, often speak of inclined passages beneath mountains, leading to spacious chambers where communities weathered long winters. While such accounts are common in highland cultures, recent karst surveys in select parts of the Tian Shan have documented deep fracture-linked voids large enough to accommodate groups of people. The surveys don't prove habitation, but they demonstrate that the environmental setting described does physically exist in those regions, making the oral accounts at least geographically plausible. With mythic references logged in a searchable format alongside modern geological data, such overlaps are easier to flag without overextending the claims. A similar care has been applied to Pacific Island traditions. On some volcanic islands, accounts speak of stone corridors, allowing inland passage during severe coastal flooding. Radar imaging on one island's interior mapped a collapsed lava tube, whose seaward opening may once have offered such a route. No one can say for certain whether it is the exact feature in the story, but the alignment between geological structure and narrative outline has been sufficient to place the site on the list for careful documentation. In this way, the process treats myths as prompts for investigation, not conclusive evidence. One of the practical strengths of this method lies in its scalability. With many myths now digitized and indexed by environmental keyword, terms like heat from the floor, perpetual night, or water without wind, searches can be run against the growing registry of subsurface anomalies. When a story's described features cluster in a region where geophysical surveys have revealed cavities, that region can be prioritized for non-invasive study. This approach has already influenced where scarce survey resources were deployed in 2025, sometimes in parallel with other drivers such as conservation goals or mineral assessments, keeping work efficient and multi-purpose. The idea of myths preserving survival knowledge is not new, but what changes the discussion now is the ability to directly test the fit between story and site. Low-frequency imaging can distinguish between dense rock and open space even at depth, while gravimetric readings can signal density changes suggesting a large void. These data streams, when aligned with persistent mythic descriptions, have sometimes led to fieldwork whose results validate at least the geological plausibility of the narratives. Among the small successes this year was a site where such combined cues led to the detection of a lateral tunnel ending in a larger cavity. The space remains partly blocked by debris, but its scale is consistent with the type of shelter described in the related account. Even when surveys return no structural match, the exercise has value. Disproving a specific link refines the dataset, helping to distinguish between recurrent symbolic motifs and those with a stronger environmental basis. Over time, patterns may emerge showing that myths from regions with certain geological conditions more often reference features testable in the field. This in itself could inform future field planning or heritage preservation decisions. From a broader anthropological viewpoint, considering these narratives as functional memory tools offers a plausible bridge between cultural tradition and empirical science. In societies without widespread literacy, memorable imagery was essential for transmitting practical information. The conceptualization of certain caves, lava tubes, or glacier tunnels as guarded underworlds or sacred chambers could have served as a way to ensure the knowledge of their location and qualities endured. Stripped of literal supernatural interpretation, these descriptions can still function as geographic markers, if one knows how to decode them. Greenland's Wolfland findings help ground this perspective, because they demonstrate how stable subterranean environments can archive environmental evidence over vast timescales. If ancient observers recognized even a fraction of that stability, through unchanging air, constant temperature, or permanent darkness, they could have woven these constants into stories that lasted generations. That insight reframes some myths not as hazy allegories, but as cultural packaging for very specific environmental encounters, ones that can now be compared directly with mapped sites. This line of research remains cautious, and for good reason. Many myths will never correspond neatly to a physical location, and many anomalies will turn out to have no connection to historical accounts. Yet the overlaps that do occur are sufficient to keep the collaboration between geologists, archaeologists, and folklorists active. For each potential match, the sequence is methodical. Log the account, note the described features, check for known structures, and if warranted, schedule survey work. In balancing respect for cultural heritage with technical investigation, the process builds a framework where neither discipline claims more certainty than the evidence supports. Increasingly, this multidisciplinary approach is prompting specialists to re-evaluate long-standing material in their own archives. Stories dismissed decades ago for lack of proof are being reconsidered now that tools can probe far deeper and with greater resolution than before. Maps, seismographs, and radar returns feed into the same databases as transcribed accounts, allowing for connections no single researcher could spot in isolation. Over time, clusters of data points, mythic and geological, begin to take shape, offering possible explanations for why certain descriptions are so persistent in specific landscapes. For those working at the intersection of myth and geology, the greatest value is not in confirming or denying individual tales, but in building a shared investigative map of the underground. Each recorded correlation improves the odds of making the next one more efficiently, and each null result tightens the focus of the search. What is taking shape is an iterative cycle. Tradition inspires survey, survey refines tradition's context, and both feed back into a larger picture of how humans have interacted with the planet's hidden structures. Having this growing set of environmental clues, whether drawn from present-day maps or centuries-old narratives, inevitably shapes where eyes and instruments turn next. In some cases, those targets are in terrains relatively easy to reach. In others, the areas of interest lie well beyond the range of direct human access, where researchers must rely on indirect readings and specialized instruments to detect what cannot yet be approached. And it is in those harder-to-reach layers of the Earth where some of the most perplexing signals have begun to emerge. Seismic echoes from the unreachable depths. Earlier this year, a network of deep-ocean seismic stations, set up to monitor long-term tectonic trends, logged a sequence of low-frequency waveforms unlike the typical signatures of earthquakes or volcanic tremors. The station that first recorded them operates in one of the most geologically quiet oceanic zones, positioned far from major plate boundaries and isolated from surface vibration sources such as shipping lanes. The initial readout showed a drawn-out, rhythmic reverberation rather than a sharp jolt, and its slow pulse rate placed it outside the range of most shallow seismic disturbances. Technicians verified within hours that the anomaly was not the result of instrument malfunction, and the data was flagged for broader scientific review. Once the signal was processed using high-resolution analyses, patterns emerged within the waveform that differed from those produced by known deep mantle activity. Certain bands of frequency weakened noticeably when the waves would be expected to pass through particular depth ranges, then resumed strength in lower layers. This pattern did not point to a single explanation. In current geophysics, such changes can be consistent with variations in density, complex layering, or even pockets of partially molten rock. These conditions can alter wave speed or direction in ways that may superficially resemble the effect of a void, But researchers emphasize that identifying true cavities at great depth remains extremely difficult. Anomalies like these are not unknown, but they are easy to lose in the constant background of seismic noise produced by thousands of simultaneous events worldwide. In the past, energy from waves traveling through the deep earth was often masked by unrelated disturbances in the crust or shallow mantle. The difference now is the availability of enhanced signal processing techniques that can isolate fainter, deeper components with much greater accuracy. By compensating for energy loss at different depths and filtering out surface and near-surface vibrations, analysts can reconstruct a clearer picture of how waves behave as they traverse the planet's interior. In this case, the refined data hinted at a zone with properties deviating from surrounding rock, possibly less dense or more fractured, but without definitive shape or size. The variations did not persist for the multi-minute spans that would imply an enormous empty chamber, as such effects remain unconfirmed in peer-reviewed studies. Instead, the measurements suggested a localized region influencing the wave paths enough to merit additional scrutiny. Within the community, interpretations ranged from small-scale heterogeneities formed by past geological processes, to pockets of partially molten materials, to unusual mineral distributions that slow and scatter seismic waves differently than expected. Debate over what these readings represent is informed by other recent developments in seismology. For example, studies led by John Vidal and colleagues have used precise measurements of seismic wave arrival times to propose that Earth's inner core may alter its rotation speed relative to the mantle and crust over decades. That conclusion would have been hard to sustain a generation ago, before high-density seismic networks and advanced timing algorithms made such subtle changes detectable. The same principle applies here. Carefully analyzed anomalies can reveal internal complexity far beyond the simple concentric shell models still common in diagrams. Not everyone is ready to assign this year's deep ocean signal to an unusual geological structure. Alternate interpretations note that temperature gradients or compositional shifts within mantle rock can produce very similar effects on waveforms, without requiring the presence of low-density pockets. Others warn that even with improved filtering, rare noise combinations can mimic the signature of deep anomalies. Still, most agree that repeated detection from multiple stations strengthens the case for a persistent feature in the broad region of interest. In fact, similar wave behaviors were recorded from another part of the same ocean basin network weeks later, prompting targeted follow-up. One reason the location attracts attention is its apparent distance from present-day volcanic ridges, subduction zones, or other deep crust activity centers. These quieter environments are often selected for baseline measurements precisely because they allow subtle anomalies to stand out. So detecting one here raises the possibility of features unrelated to current tectonic processes. Some geologists suggest that the site could preserve remnants of early mantle structures, material boundaries or mineralogical transitions locked in place billions of years ago, that happen to affect seismic waves more strongly than their surroundings. The tools for studying such features are evolving rapidly. Machine learning systems, trained on massive datasets of catalogued seismic events, can now flag departures from expected patterns as they occur, sometimes reconstructing likely source geometries before human analysts have reviewed the data. By running the deep ocean anomaly through these models, researchers can simulate how it would appear if detected by stations placed at other angles or distances. These synthetic perspectives help to refine estimates of the feature's extent and orientation without immediate need for physical instruments in those locations. In trials, such modeling has indicated that the zone in question could cover a larger stretch than early calculations implied, although the resolution is still too coarse for firm conclusions. Part of what makes anomalies worth tracking is their potential to refine theories about how a planet's interior works on both short and geologic timescales. While the concept of vast hollow regions is not accepted in mainstream geology, the idea that substantial low-density domains might form, persist, and influence mantle dynamics is plausible within current models. Such domains can redirect heat flow, affect deep convection patterns, or trap ancient materials, altering everything from surface volcanism to magnetic field behavior. Still, turning raw seismic variation into specific geological models requires further, corroborated data. That need for replication and cross-check drives plans now being discussed among oceanographic and seismological teams. Controlled source experiments, where known energy pulses are generated and observed across multiple stations, could help distinguish between density changes, compositional layers, and other factors contributing to the anomaly. These efforts demand significant coordination and resources, deploying or servicing instruments at extreme depths, and aligning measurement campaigns across international networks. Yet they represent the most direct way to test whether recurring wave patterns are artifacts of measurement, byproducts of ordinary mantle variation, or actual signatures of unusual zones.